have we known each other like now 1, 2 years, 3 years?
Yeah,
It's like,
not quite.
Not quite. So I got to know Chris because he got one of these DOE computing fellowships, and then he was supposed to come out. Was it like March of 2020, something like this?
Yeah.
And then that didn't happen, and then we postponed it for a year so he could come out for real, and then he did finally his fellowship virtually in 2021. But we've stayed in contact, so he's been working with us a lot sort of on the quantum computing side. He is a student in Arizona working on traditional lattice field theory with Stefan Meinl, but he's been interested in quantum computing for a while, and he's been working with us on computing. So I sort of feel like I'm sort of a second advisor, if you want. So it's a great pleasure to have Chris talk about some work that he did quite recently on overcoming exponential volume scaling in lattice gauge theories.
Yeah, all right, thanks, Christian. And thanks for inviting me to the organizers. And thank you all for coming. Yeah, so Christian sort of did the title slide already, so now we can go on to the next one. Okay, all right. Yeah, so I have to accept being recorded first. Okay. You did not see that part. All right. Great. Okay. Yeah. So this is a broad overview of the talk. So for the first section, we're going to motivate quantum computers and why we are excited about them for high energy physics and nuclear physics. And then from there, we will review the particular U1 formulation that we actually try to implement on a quantum computer. And once we've done that, we can then talk about the gate count scaling required to implement time evolution of this theory and talk about an exponential volume scaling that appears. And then we'll talk about how to actually overcome this by performing a change of operator basis. And then once we've done that, we'll conclude by talking about this procedure we use to actually build the circuits that could be implemented on quantum computers. So starting with the motivation. So I guess if we want to fully understand the standard model, we need to be able to study strongly coupled theories. And within these theories, there's rich phenomena of non-perturbative physics. And this is a really profitable place to look for new answers to big questions. And there are certain non-perturbative properties of quantum field theories that have sort of eluded all attempts to study with classical computers. And these are real-time dynamics. These are 2 examples. So studying how some system evolves in time, and then also studying physics with finite density, so using a non-zero chemical potential. And so in order to more motivate the need for quantum computers, we can go in a little more detail as to why these are hard to do classically. And so when we think about solving for the dynamics of a quantum field theory in a non-perturbative way, what we mean is solving the path integral numerically. And so the procedure is you put your theory on a lattice, as sort of shown here, and then you would, the resulting path integral is some very high dimensional integral. The only practical way to solve this is using Monte Carlo methods and importance sampling. However, if you notice, looking at this pink term here, exponential of I times your action is a complex number. So this is not positive definite, and it's also highly oscillatory. So these properties mean that if you do some sort of resource counts and see how much classical computing resources you need to solve this, you find that it scales exponentially with the volume. And so this exponential volume scaling is prohibitively expensive, meaning we can't really study real-time dynamics except for the very small lattices. And so we can't extract interesting physics in this way. And so it might also be worth pointing out that people in lattice QCD, for example, solve the path integral all the time. And how come they can't get real-time dynamics? So to sort of review that and show what the difficulty is so for Euclidean lattice gauge theory, the main idea is you want to do a Wick rotation. So you perform your calculation in imaginary time. So you replace t with some imaginary, or some I times tau, where tau is real. And then if you work through this and plug in this value and replace t everywhere with I tau, you instead get this Euclidean action here in blue. And this Euclidean action is a real number, and it's positive. And then so exponential of minus the Euclidean action has all very nice properties of a probability distribution. And so what this means is that you can solve the Euclidean path integral numerically using Monte Carlo methods and importance sampling. So there's no sign problem here. But the caveat is that because you are working with imaginary time, you cannot access real-time observables. So even though lattice QCD can calculate all these very nice things, it doesn't suffer from the sign problem. You cannot use it to calculate real-time observables. And so this difficulty is one reason why people are very excited about quantum computers and maybe their potential ability to overcome the sign problem, if you will, and allow for studying time dynamics non-perturbatively. And so we're very excited about this. And to get maybe just a brief introduction to quantum computers. So a quantum computer, instead of storing information in classical bits, you store them in quantum bits. And so these are two-state systems. They can be in any superposition of a 0 state or a 1 state. And you can change the state of your qubits by applying quantum gates, and these are unitary operations. And once you are done, at the end of the day, you calculate whatever you're interested in by measuring the state of your qubits after acting on them with gates. And so a typical quantum calculation, they represent these in terms of quantum circuits. It's a nice way to visualize what you're doing. And so if we want to think about if quantum computers can overcome the sign problem, the relevant costs for any quantum calculation are the number of qubits that you need to achieve the precision you want, and the number of gates you need to act on your system in order to perform time evolution, for example, and then also how many measurements you need to do. Okay, and so how would this look for a sort of lattice gauge theory simulation? So there's sort of 3 steps in a very schematic way. So the first step in any calculation is you have to prepare whatever state you're interested in. So this is initial state preparation, this step here. And then once you've prepared your states, you then need to time evolve it. So you apply the time evolution operator, this exponential minus I times the Hamiltonian times time. And so you decompose this operator into gates. You act it on your initial states. And then at the end, you measure whatever you're interested in. And so maybe it's worth noting that steps 1 and 2 sort of have comparable complexity in terms of resource costs. Step 1 being generally slightly more expensive than step 2. And also it's worth pointing out that sometimes you don't even need step 2 if you're just interested in certain properties of ground state, for example. And so the question that we want to answer is that, is it possible for a lattice gauge theory to perform a calculation like this one, such that the cost in terms of the number of qubits, gates, and measurements scales only polynomially with the volume? And if this is true, then we can, in principle, we have a chance of simulating real-time dynamics with quantum computers. And so this is the question that we want to answer. And so how are we going to go about, answering this question? This is not an easy question to answer. And so this is sort of, as we think about how we would do this, we're going to use as a guiding principle that quantum computers are very much in their infancy. We have no idea what they're going to look like 30 or 40 years from now. And so we need to think carefully about how we can use quantum computers to do what we need. And so there are sort of 3 areas that need to be worked on simultaneously. The first is theoretical development. So how do you actually formulate quantum field theory in a way that is compatible for study with quantum computers? And so within this category falls the task of writing down Hamiltonian with nice properties that you can use to do the time evolution. And then you also need to think about algorithmic development. So how do you actually map your quantum, your like time evolution upper onto gates in an efficient way? And then also which quantum hardware is best suited for your particular problem. So there are different kinds of hardware, for example, qubits that are superconducting circuits that IBM is pushing for. And then there is also people who use cold atoms as their qubits. And these different hardware have different pros and cons, and you need to consider which one is best for you. Okay, and so now that we sort of have set the stage, we can state the problem that we've been working on slightly more precisely. And so as the Holy Grail, we want to get to QCD, but along the way, we start with U1 gauge theories and build up from there. So this talk, I'll be telling you about how the gate count scales for simulating a pure U1 gauge theory in 2 spatial dimensions using Suzuki-Trotter methods to do the time evolution. And if at the end of this talk, you only take away 2 things, the 2 things we would like you to take away are that naively implementing this using only physical states in your Hilbert space has a cost that is exponential, scales exponentially with the volume in terms of the number of gates you need. And this exponential volume scaling is just as prohibitively expensive as it was for classical computers. And so this would make simulations with a quantum computer impossible. And the second main takeaway point is that this exponential volume scaling can be broken by performing a carefully applied change of operator basis. Right, so yeah, keep these in the back of your mind as we go through this talk. Okay, and so that was sort of the motivation. Now with that out of the way, we can talk a little more in detail about the actual U1 formulation that we're going to simulate. Okay, and to start this discussion, we're going to talk about gauge invariance and Gauss's law. So the continuum theory, so for just a pure gauge theory, it's an integral over the electric and magnetic fields, but these fields are subject to additional constraints. So for example, the electric field has to satisfy Gauss's law, and the magnetic field has to have zero divergence. And so one thing about some general Hamiltonian that you write down is that the Hamiltonian, the Hilbert space here, this is my schematic of a Hilbert space, can contain both physical and unphysical states, where physical states are defined to be states that obey Gauss's law. So if you take the divergence of your electric field, subtract the charge density, and act down your states, if you get zero, it's a physical state, and it's in this orange blob. And if it's you don't get zero, it's an unphysical state. And so the fact that the Hilbert space sort of contains both physical and unphysical states has some disadvantages. It could lead to some issues when doing a quantum simulation. And one of these issues is that this basis of states that you're working with is overcomplete. And so simulating these extra states in the Hilbert space requires more quantum resources than strictly necessary. And another one that's sort of important for noisy quantum computations is that because your Hilbert space contains these sectors, you can actually get charge violating transitions in your quantum calculation. And to see a simple example of how this might happen, we're going to think about some example where we have the Q equals 0 sector. So total charge 0 is like the sector that we're interested in, the physical space. So our physical states live in this orange blob here. But the Hilbert space also contains sectors with net charge -1 and net charge +1 and all other net charges. And so as you do your calculation, let's say you initialize your state at t0 in your physical Hilbert space. And if you were to do the calculation in time evolve and in a noiseless quantum computer, you would stay within this Hilbert space. But as you are time evolving, say, you get quantum noise from your quantum computer. So there's some interaction with the quantum computer and its environment in an uncontrolled way. And that can actually kick you out of your physical Hilbert space and cause a charge violating transition. And so these are sort of two issues that can happen when you're dealing with such a Hamiltonian. And one example of such a Hamiltonian is the Kogan-Susskind Hamiltonian. So this was one of the first Hamiltonians written down for a gauge theory. And so it's formulated in terms of electric links. So these live, they connect the sides of your lattice. And then it's also formulated in terms of plaquettes. And so these plaquettes are just products of gauge links around some small closed loop in the normal definition. And so a lot of work has been done recently to try to write down a different Hamiltonian that contains only physical states in the Hilbert space. And these are broadly known as dual bases formulations. And so you actually formulate your Hamiltonian such that the Hilbert space does not contain unphysical states. And then you would not have these issues that we talked about before. And so as we go through, if there's anything, if I'm going too fast or something's not clear, please stop and ask questions also. Okay.
So just a very naive question.
Yeah.
This second problem is only a problem when you actually simulate this into a real quantum computer, right? If you use some kind of classical computer to simulate the dynamics, this is not an issue.
Yeah, so without noise, you would stay in your physical Hilbert space. So the second problem would only happen in a noisy quantum computer. So like when we're dealing with NIST computers, fault tolerant quantum computing is a long ways away. So this will be a problem for some time.
You can simulate noise too.
But you can also, you can simulate noise, yes. But yeah, this would not be a problem.
There's actually one other thing is that I think that Jesse Stryker pointed out is that if you do the exact Hamiltonian, then it is correct. But you use an approximate, you use a Suzuki-Trotter approximation. And I think what he pointed out that even that approximation can kick you out
I see.
of the space.
Yeah, that's a great point. I should have looked at that. Thanks. Okay, and so we can talk a little bit more about dual bases now because this is one that we're going to implement. So the general idea is to work with a gauge redundancy-free formulation of your theory. So we work with Bloquet variables, so we replace the electric links with these rotor variables, these things are. And so with zero charge density, this is what we're thinking about, right, pure gauge theory. You define these rotors such that if you take the curl of them, you get back the electric field. And so what this means is because the divergence of a curl is zero, Gauss's law is automatically satisfied locally. And so there's another nice property that we'll use later is the fact that the magnetic field and the rotors are conjugate variables. So you can think of the magnetic field as like x and the rotors as like p. And so you can change the bases to where one is diagonal using a Fourier transform. So we'll use this when we do our quantum simulation. But yeah, so if you write your Hamiltonian down, just making this change, you replace your electric field with these curls of rotors. And so you have an electric Hamiltonian and a magnetic Hamiltonian. And we have cosines of magnetic field operators here. So this G here is also the gauge coupling, just something to know going forward. Right, but so this formulation satisfies all of the local constraints automatically, just because we've written our rotors like this. However, there is a remaining global constraint that has not been satisfied, and you can figure this out by counting the numbers of degrees of freedom you need to specify a state in your Hilbert space, and you find if you do this counting, that you have one redundant degree of freedom, and this comes from the fact that the product of Bloquets around a closed surface has to be the identity, which is just a fancy way of saying that the sum of the magnetic fields has to equal zero across the entire lattice. So it has to have zero divergence through any closed surface. And so because we want to work with a gauge redundancy-free formulation, our workaround for this is to just enforce the constraint at the level of the Hamiltonian. So we write one of the magnetic field operators as negative the sum of all of the others, and we set the associated rotor to zero. And so the electric Hamiltonian does not change much. It just has one less rotor, but the magnetic Hamiltonian actually becomes quite different. So we have these original terms, which are cosine of a single magnetic field operator. But then we also have this term here, which is a cosine of the sum of all of the operators. And so that term is highly non-local. It couples the entire lattice together. And so what we'll see is that this is actually the source of the exponential volume scaling. And we'll show that later. But also another thing, so some notation is that this NP we use as the number of independent Bloquet variables on the lattice. And so this is sort of the same thing as the volume for us. So NP and volume are used interchangeably. Okay, and so to summarize, this is our gauge redundancy-free formulation of a U1 Hamiltonian. And so now that we have this, what we want to do is to build a time evolution operator so we can simulate time evolution. Okay, and the first step to doing so is thinking about, well, how do we actually represent these operators R and B in terms of quantum gates? So this is sort of the next thing we're going to talk about. And the way that we do that, we're going to use a digitization scheme that Christian and then Dorota came up with. So these operators, in the basis where they're diagonal, so they're represented by diagonal operators with evenly spaced eigenvalues on the diagonal. And if you take each lattice site and represent it using little nq qubits, then it is known that you can write operators of this form as a sum of poly Z matrices. So this sigma Z is a poly Z matrix acting on the jth qubit. Was it no hands there?
No, because it's touch sensitive.
Oh, okay, sorry. No touching. Yeah, and so this is what the operators look like. They're just sums of poly Z operators with different weights in front of when they act on different qubits. And so this Bmax parameter here in purple, this is a known function of the gauge coupling, and so you tune it to minimize the digitization errors you get from truncating these infinite dimensional operators into some finite dimensional set. And so it was found that by tuning Bmax, you can get per mil level accuracy of the low-lying spectrum just using 3 qubits per lattice site. And so this will be important to remember going forward, that we can keep the number of qubits per lattice site small. Yeah, so that'll be important when we do gate counts and thinking about that in the next few slides. Okay, and so this is sort of the last slide for me reviewing the formulation that we use. So are there any questions here? Pretty good.
I mean, this observation that NQ can be 3, is this analytically determined? Like how do you know? I mean,
Right.
where does this come from?
Right, yeah, so they did numerical tests, so for a small enough system, you can diagonalize it exactly. Or actually, no, but it was in the non-compact theory, right? You knew the energies exactly. And so you can just compare to the exact energies, but also because as you increase NQ, the number of qubits per site, you expect your answers to approach the exact value. So in the limit of this goes to infinity, your numbers should approach the exact energies. And so what you do is you just compare to a very, you increase this until the answer stops changing to some very high precision, and then you call that your exact answer. But so it's done numerically. So it can only be checked for small lattice sizes. So things would have to be checked in a rigorous way, like some error analysis for large lattices on it.
So I think you can understand that the accuracy is exponential in the number of qubits. It sort of goes by, essentially because the ground states sort of fall off exponentially, there's sort of Gaussians, has to do with that. And then essentially if you were to chop off the tails, which only gives you exponentially small effects, then sort of by a Shannon-Nyquist theorem or something, you can actually argue that you get the exact answer. So you can prove that it's exponential. So the accuracy goes exponential in NQ, but then why it's 3 is a numerical.
Cool. Yeah, thanks. Okay, so that is the review. So now we can talk about and think about the number of gates we need to simulate such a theory. Okay, and so this is the time evolution strategy that we're going to use. So we want to implement time evolution operator, which is this here, the exponential, the electric plus the magnetic Hamiltonian. And because we don't know what this operator looks like, the sum of them, we break it up into small pieces. And so you incur some error because HE and HB don't commute. But you can write this as a product. Incur some small error if you do a bunch of time steps. So this delta t here, the error that you make is on the order of the size of your Trotter time step. And so you can just take many small time steps and approximate the time evolution operator in this way. And so we work in the magnetic basis where the magnetic Hamiltonian is diagonal. And so for step 1, we implement this diagonal operator, which is the exponential of the magnetic Hamiltonian. And then from there, we switch to the electric basis using the Fourier transform. And then we implement the exponential of the electric Hamiltonian in the electric basis, where it is diagonal. And then we switch back to the magnetic basis using the Fourier transform. And so you repeat this over and over again for as many steps as you need. And so now that we know how we're going to do the time evolution, we can think about the number of gates required to implement each step of this along the way. Okay, and so
does it matter which order in magnetic, electric, which one go first? I guess not. If you...
No, it might matter on for some order delta t error, but I would say no, not really. Right. Okay, and so I've changed sort of the notation here. So I've written this electric Hamiltonian now directly in the electric basis, and I've written the Fourier transforms out explicitly here. So starting with the cost of a Fourier transform, so there's a well-known algorithm that can compute the Fourier transform in a number of gates that is quadratic in the number of qubits it acts on. So because we need to implement the Fourier transform at each lattice site, that means that for each NP lattice sites, we have a gate cost of little nq squared. But for this sort of gate count scaling, we're going to focus on the scaling with the volume, the number of plaquettes here, because remember, little nq can be kept small. So the Fourier transform is a linear cost in the volume. And so now we can think about the cost of exponentiating the electric Hamiltonian, this step here. So remember that because we're taking curls of these rotors, these curls are finite differences on the lattice. When you square them, you get a bunch of sums of bilinear terms. So each term in the electric Hamiltonian is like a product of 2 rotors. So because each rotor was a sum of poly z's, a product of rotors is a sum over all possible combinations of 2 poly z operators. So the number of terms in each bilinear term is little nq squared. So to implement each of these terms, you need on the order of little nq squared gates. But the number of terms, again, scales linearly with the volume. So this term is also a linear cost in the volume to implement. Okay, so still linear in the volume. So now we can talk about the magnetic Hamiltonian. And the magnetic Hamiltonian sort of has two distinct pieces. So we have these cosines of a single magnetic field operator, and then the cosine of all of the magnetic field operators summed together. So we're going to focus on this blue piece first. So this cosine of a magnetic field operator, to figure out how many gates it's used, we're going to Taylor expand a cosine. So the cosine is a sum of poly z's. And if you Taylor expand this, you get all powers of this sum, which means you get all possible combinations of products of poly z operators acting on these nq qubits. And so the number of terms in this Taylor expansion is 2 to the power nq. So implementing each of these can be done in roughly this many gates for each term. And so because there is one of these for each lattice, this term is also linear in the volume. And just remember that this little nq can be kept small. So exponential in a small number is fine. We're happy with that. 2 to the 3 is only 8. So that's not a big deal. And so we are still linear in the volume. And now if we look at this other term, that is the sum of all possible magnetic field operators on your lattice, you do the same thing, expand using a Taylor series, instead of, and now you find the number of terms scales exponentially with the volume in this because it couples together every term on your lattice. So you have an exponential number of terms in the volume you need to exponentiate. And so therefore the gate count scaling for this term is exponential in the volume. And so to summarize, everything was linear except for this one term. So this exponential volume scaling, where NP is the number of plaquettes, comes from this maximally coupled term here in purple. And so, maybe not surprisingly, exponential volume scaling is killer. If you do a 20 by 20 lattice, for example, you need to the order of 2 to the 400 times little nq. So whatever little nq is, this term is just not going to be possible to simulate on any quantum computer.
So naive question, is this is the scaling with exponential of the volume a general property of Hamiltonians that have a non-local term? Because you mentioned that this term is non-local, right? You get it from the imposing the Gauss law. Is this a general property dealing with this kind of Hamiltonians?
Certainly for one as complicated as the cosine of this, but for example, if you just had this squared, then it would be sort of quadratic in the volume because you wouldn't get, if you just take the sum and square it, you only get bilinear terms. So you only ever have cosines of like magnetic operators times at two sides. But because this cosine contains sort of all powers of the sum, you get all possible like terms without products over the entire lattice.
You have a Zoom or Zoom question.
Oh, there's a Zoom question.
Yeah, sure.
For naive question, where you get the cosine here?
Yeah, okay, great. That's an important question. So where is it? Sorry, okay. So the cosine comes from these plaquette terms. So each plaquette is the exponential of I times a magnetic field operator. So if you take e to the minus IB plus e to the IB, you get cosine of B.
Okay, got it. Thank you.
Sure. Yeah.
But if you put in more, so is there a way, so if you put in enough lattice sides, is there a way to implement instead of boundary conditions where the magnetic field dies off on the borders so that you don't have a global constraint?
So for sure, if you have open boundary conditions, this constraint is not present. And I haven't thought about this possibility where at the edges maybe it decays.
Right, like you're still putting it on a torus, but just making sure that that the initial state is such that even if you put in enough trotharizations, the thing still remains localized.
Yeah, that's an interesting thing to think about. I haven't thought about it yet.
But I would think that the magnetic field dies off fast enough that probably, that defines your volume. Like, wherever the support of your magnetic field is, maybe that defines your volume.
Right.
And so it's still exponential in the volume of support of the magnetic field, right?
No, because there's no term. there. There's no cosine of the sum of the BPs.
Oh, I see, because you're saying that you just said one of them too, yeah, maybe.
Yeah, interesting to think about. Yeah, good question. Thanks. Oh, that's too far. Right. Okay. Yeah. So now that we know sort of where this exponential volume scaling comes from, we can think about how to break it. And this will be done by performing an orthonormal operator basis change. And the general idea is you want to do a change of operator basis such that no cosine in your magnetic Hamiltonian contains more than a number of terms that is logarithmic in the volume. And if you can do this, then you'll break your exponential scaling. And so I'm going to show some sort of technical details of this operator on this slide, but the technical details aren't really that important. We're going to do an example for a small lattice afterwards to hopefully explain better, just by going through this example. But just know that we have a way to do this for arbitrary lattice sizes, and then we'll go through an example afterwards. This change of basis, this script W, is a block diagonal matrix with a number of subblocks on the diagonal that scales logarithmically with a number of plaquettes. And then another property is that each of these subblocks can't be too big and it can't be too small. And the third property is that the first column of every one of these matrices has to be equal to a constant. And if you do these three things simultaneously, you find that this maximally non-local term in this new basis now requires a number of gates that's polynomial in the volume. So this will break the exponential volume scaling from the maximally coupled term. However, we need to be careful that we don't reintroduce an exponential volume scaling in this previously local terms by doing this change of basis. And so this can be avoided by making sure that each row of these matrices on the diagonal has a certain number of non-zero elements. You have to limit the number of non-zero elements. And if you do this, these previously local terms cost more, but they are still polynomial in the volume. And so to sort of summarize the final gate counts after doing this transformation in this new basis, implementing this weaved magnetic Hamiltonian, so this is what we call this new operator basis. And we call it that because of how we generate these matrices. It's just the name we chose. But in this new basis, we find that magnetic Hamiltonian has a cost that scales linearly, or not linearly, sorry. It scales polynomially with the volume, where the power of this polynomial is given by the number of qubits per second. And this breaks the exponential volume scaling by doing this change of basis. And so now we can go through an example to show how this would work in practice. So we're going to think about a 16 plaquette example. So this is a small lattice, but it's very good for understanding how this works. So remember that this was a block diagonal with the number of subblocks being logarithmic in the number of plaquettes. And so for us, that means that we want 4 subblocks on this matrix. And the next property was that each subblock had to have a certain dimension. And if you plug in the numbers, we find that each of these subblocks is a 4x4 matrix. And then another property was that the first column of any one of these entries had to be a constant. And so if you do that for us, the first column of each of these matrices on the diagonal is equal to 1/2. And then the last property was to make sure that these weaved matrices on the diagonal have no more than a certain number of non-zero entries per row. And so for us, we need to make sure that there are no more than 3 non-zero entries. And so we see that each row here has at least 1 0 in it. And so this is the change of basis that we're going to use for the 16 plaquette example. So now that we have our matrix, we can do the basis change. And so one important thing is that this is done on pen and paper before you digitize the theory. So what we do is this column here, these B tilde, these are the magnetic field operators we want to express our Hamiltonian in terms of. So you take this column of all of your 16 magnetic field operators, you multiply it by your weave matrix, you see this nice block diagonal structure. And then you express your magnetic Hamiltonian in terms of these operators. And then once you have done that, you then digitize using a similar procedure that we talked about before, representing these things as sums of polizes. And so then once you do that, you can simulate and it will be polynomial in the volume. And I think there's a nice way to understand how this is broken to polynomial visually. So that's what we can talk about next. So on the left, we have the original basis, and on the right, we have the weaved basis. And so this is a lattice, and so each operator represents one lattice site or one magnetic field operator. And so I'm going to use boxes to represent each term. So this blue box here indicates that the number of terms inside a box is the number of magnetic field operators that appear in a single cosine. So each of these blue boxes correspond to these local terms here. So these were not hard to simulate. Remember, these were cheap. And then this term here couples the entire lattice together. And this was the source of the exponential volume scaling. Okay, and if we do some simple numbers of guessing how many gates it would need, or approximating, if you use 2 qubits per site and plug in 16 plaquettes, you need roughly 10 to the 9 gates in order to do a single Trotter step for this very tiny lattice. And now we can do the same thing for our weaved magnetic Hamiltonian. And the first term we're going to look at is this term here. So this red term was the previously maximally coupling term, but in this new basis, we see that it only couples together 4 operators. So this is a cosine of the sum of B1 plus B5 plus B9 plus B13. And so that's sort of the breaking of exponential volume scaling can be understood visually by the fact that this only contains a number of terms that's logarithmic in the volume. So it doesn't couple the whole lattice together anymore. But if we look at what these previously local terms now look like, so they now each contain 3 magnetic field operators. So these boxes with different line styles are different cosines. So for example, there would be a cosine of 07 plus 08 plus 05, and then another cosine with 06 plus 05 plus 08. And so if you do another estimate of the gates required, plug in 2 qubits per plaquette for 16 plaquettes, you find that you need, instead of 10 to the 9 gates per step, you need roughly 100. Okay. Are there any questions with the change of basis? Is everybody sort of happy with where we're at?
The wave matrix, where did that come from? Did you guys just did you just propose one and?
Yeah, there was some experimentation, yes. And then we found that certain Hamiltonians were easier to simulate than others. And then in the end, Dorota came up with this very nice way of formalizing it and writing it down. Yeah, but it started with playing around and sort of observations about some Hamiltonians that were easier. But,
I think we give a proof at the end that
yeah,
you can construct a matrix that has these properties, that it has logarithmically many blocks. Each block is only logarithmically big. And the number of zeros is also scales logarithmically. So, or the number of non-zero entries scales logarithmically in each one. So that sort of proof. I mean, you could prove that this is true.
Those properties, at least the properties, come from the experimentation with Mathematica that you realize that you could get this.
Yeah. So I don't think we have a.
We just noticed some terms were cheaper than others, and then eventually formalize it into.
So I think we have an existence proof. We don't have a, there's probably other constructions we can do, and I don't think we have a generic,
But that sounds pretty cool though.
So it exists. You only need one, right? So.
Right. That sounds cool.
But then the complexity of finding that is still logarithmic.
To actually count.
If you have an existence, but you need to actually.
Yeah.
Find
So
one for
the classical computational cost to get that to do the weave transformation is also logarithmic. Yes.
Yeah,
it's crucial.
it's like linear and long or something. So it's pretty easy.
I understood that there's a mathematical proof that there exists this kind of basis changes, but how this illustration changes for larger number of the brackets.
Sorry, how does what change?
How this illustration? There's a intuitive understanding of how the number of I mean, yeah, how the exponential growth is suppressed in this case of the number of brackets 16. But I can imagine the illustration for larger number of brackets.
Yeah, I think you would get, so I don't know if I could draw it, but you would get similar patches where like only certain pieces, like only this quadrant interacts with itself, and then this quadrant interacts with this one, but it's coupling here. I don't know. I mean, you could just based looking at the structure of the weave matrix sort of tell which operators are interacting with each other, but yeah, I'm not sure if there's a really nice way.
I think one important thing is that if you go back to your matrix, the basis change matrix is only linear in the volume, right? I mean, the dimension of that matrix is linear in the volume.
Right.
So this is why you can do this. And to find that matrix, it's also linear in that volume. So this classical computation is, I mean, even if, you know, what do you have, like 20 by 20 lattice, there's 400s. Okay, it's a 400 by 400 matrix.
Yeah,
we can work it out
very,
easily.
very fast, yeah. Okay, and so now that we have this weave basis, for a sanity check, we would like to make sure that it sort of maintains the nice precision properties as the original basis, where we can calculate, I'm using only a small number of qubits per site, and still maintain a good precision for these energies. And so to test this, this is what this plot shows. So remember the polynomial of the gate count of the volume is the number of qubits per site. So we need to keep this small. And if we can keep it small with a high precision, that's good. So what this plot here shows is the relative error of the energies in the two bases. And so these are just different energies. So this 0 is the ground state energy, and then 1 and 2 is first and second steady state, and so on. And so this was for just 3 plaquettes, so a small system. And these different colored lines are different number of qubits per site. And so we see sort of this exponential convergence here, as expected. And then if you look at these solid lines and compare, these are in the original basis, and then these dashed lines are in the weaved basis, and we see that for the same number of qubits per site, their precision is comparable with each other. So we find that we still maintain the efficiency of the representation in the weaved basis. So this is a nice sanity check for us going forward. Right. And so that's sort of the conclusion of this change of basis, and then we're going to move on to how we actually construct our circuits from there. I think I'm doing okay on time. Yeah, so now on to constructing the quantum circuits. And this falls under the sort of the area of developing the algorithms to do this. So we now have our theoretical development, we've written down Hamiltonian. How do we actually implement it? And so this is the same slide I showed before, is the strategy we used to do the time evolution. And if you notice that aside from the Fourier transform, what we need to do is implement diagonal matrices, right? It's because we implement these in the basis where they are diagonal. So we need an algorithm to implement diagonal matrices. And there is an algorithm to do this without using ancillary qubits or things like that. And it's what we call the Walsh function formalism. And so in the next few slides, I'm going to talk about some more details of this just for completeness, but you don't need to know all of the details. Just know that if you give this Walsh function formalism a real diagonal matrix, you can turn the crank and it will give you the quantum circuit for the exponential of I times your diagonal matrix. And it can do this in a known number of C0 gates and RC gates. So for an arbitrary n qubit Hamiltonian, you can do it in 2 to the n minus 2 C0 gates and 2 to the n minus 1 RC gates. Okay, so this is the algorithm now I'm going to talk about in a little more detail. So yeah, we want to build a diagonal matrix. And so we're going to use this notation W hat I to be the ith Walsh function. And so these Walsh functions are completely analogous to a Fourier series. They form a complete basis for real functions, and you can expand any real function in terms of these Walsh functions. And so they are just, instead of like smooth curves like Fourier series, there are these sharp, they take on values plus or minus 1 on the diagonal. And the exact form of each one is not that important. But So what we're going to do is write our Hamiltonian as a sum of these Walsh functions. And for an n-qubit Hamiltonian, there are 2 to the n of these Walsh functions. And these Walsh coefficients here can be calculated in a very analogous way to how you would calculate a Fourier coefficient. You can calculate them using the orthogonality relations of the Walsh operators. And so you calculate them in this way. You take the Walsh operator, multiply it by a Hamiltonian, take the trace, and with the proper normalization, you can calculate these coefficients. And once you have all of these coefficients, the next step is to write your time evolution operator as a product of these exponentials of Walsh coefficient, or these Walsh functions here. And so what does one of these Walsh functions look like on a quantum circuit? So for an example, if you have a 3-qubit circuit and looking at the 6th Walsh function, so mathematically, you can write it down as the identity tensored with the poly-Z matrix tensored with another poly-Z. And the quantum circuit for this is here. So it's a Z gate wedged in between 2 C0 gates. And now if we want to exponentiate this, it can be done in a straightforward way. You just replace the Z gate with a rotation gate around the Z axis. And then the phase is just -2 times the Walsh coefficient. And so this can be generalized for arbitrary number of qubits, for arbitrary Walsh function, and then you can build your time evolution operator using these. And so that's how you would build it exactly. But there's another nice property of this formalism in that it allows for a very natural way to approximate a quantum circuit if you don't need some perfect implementation. And so this is, again, sort of analogous. You can think of these as having the same properties as a Fourier series. So this Hamiltonian is expanded in terms of Walsh functions, and each Walsh function has a weight, these Walsh coefficients. So if this coefficient is small, then what this means is that it doesn't contribute all that much to the Hamiltonian. And so you can drop it with introducing some controlled error. And so you can then build an approximate circuit by dropping things with small Walsh functions or Walsh coefficients. And the procedure is you calculate all of these coefficients, and then you pick some cutoff, say, okay, I want to drop all things with below some theta min. And then once you've done that, you can simplify the C0 gates in your circuit. And in this way, you'll get a circuit with less C0 gates and less rotation gates for some controlled error that you introduce. So there's one caveat with this method is that there are an exponential number of Walsh coefficients in the size of your matrix. So if you want an n-qubit matrix, you need to calculate all 2 to the n Walsh coefficients. So there's a way to do this. The classical cost scales exponentially because you need to calculate an exponential number of these. But this is not a problem for us. This is sort of the weak basis in how it solves the problem. So because all of our cosines contain only a logarithmic number of operators in the volume, the size of any matrix we actually have to implement is logarithmic in the volume. So this n is always logarithmic in the volume for us. So it's a polynomial cost for us. So we also avoid this exponential classical cost. And to give a little intuition for how this can simplify a circuit, here's a simple 3-qubit example. So this is how you build an arbitrary 3-qubit diagonal unitary matrix. And so it's sort of rotation gates with alternating C0 gates here. And so in this example, let's assume that we've chosen some cutoff. We're going to drop all rotation gates. So the rotation gate 3, 7, and 5, we're going to drop these from our circuits. And so the resulting circuit looks like this. But now at this point, we see that we can actually simplify the C0 gates. So this here, because the product of 2 C0s is the identity, we can just drop this completely. And then we can use properties of C0 gates to commute this past this one and drop 2 of those 3. And so after simplifying these C0 gates, we get in the end our approximate circuit that instead of having 6 C0s, now in the end of the day only has 2. And so this is sort of how the C0s get reduced when you approximate your circuits. Okay. And so now that we understand how this approximation works, we can look at an actual gate count for our magnetic Hamiltonian in the Weave basis. Yeah.
How are you deciding which gates you're dropping when you do this?
Yeah, so for this example, I just chose them.
Yeah.
But how we choose them is we say, okay, I want to drop all rotation gates with a small angle. So I pick some cutoff, say 10 to the minus 3. They say if there's an angle that is less than that, I drop it from the circuit. Yeah, and then yeah, so based on how much error is acceptable for you.
Do you have to change the cutoff depending on how long the string of gates is? Like accumulating some like random walk of total phase that you dropped. If you drop like 1,000 gates, and each one has an angle less than 10 to the minus 3, you're still accumulating like an O1 phase walk.
Yeah, so the rigorous error bounds for this method, I think, are hard to do because of this reason that you said. It's not easy to figure out, if these errors add coherently or incoherently. So, because these Walsh coefficients can have different signs, sometimes the errors, in general, they don't add linearly like that. But yeah, this is still something that needs to be understood better for like an actual calculation. Okay, yeah, and so here is a plot. So what this shows is the number of CNOT gates required to implement the exponential of the magnetic Hamiltonian in the weaved basis. And so we're using 3 qubits per site. And so number of CNOT gates on the y-axis and as a function of the number of plaquettes on the x-axis. And so these different colored lines correspond to different values of this theta min. So as you go down here, we're dropping more and more gates because we've increased the minimum angle that we keep. And so for reference, these gray lines here are just different polynomials of the volume. These are just reference. So if we look at, for example, this blue line first, this is theta min equals 0. So we make the circuit exactly. And as expected, we find that the scaling is actually polynomial in the volume, like we showed. But then we find that, for example, as you increase your theta min, so we chose theta min to be proportional to the Trotter step size here in this example. And we find that, you can reduce the scaling by up to, power of the volume using this approximation method.
How good is that? I mean, as you drop more and more, and then your approximation probably will.
Yeah,
will suffer, right?
It will, yes. And we did a sort of simple analysis of this in our paper for a small system, but this does need to be, I would say, studied in more detail. Yeah. Right, and so with that, we can sort of zoom out and summarize what we've talked about. So we found that we know that classical computation of real-time dynamics and finite density properties of quantum field theories is not possible to do because of this sign problem. And we're hopeful that quantum computers can potentially overcome these problems. And then we talked about different Hamiltonians you can write down and certain advantages and disadvantages. And we found that some Hamiltonians allow for charge violating transitions because they contain both physical and unphysical states. And then we said, okay, to overcome these problems, we want to work with a Hamiltonian that is free of gauge redundancies to avoid these problems. But we found that simulating time evolution in this U1 gauge theory had an exponential number of gates in the volume. But then we showed that we could break this exponential volume scaling by performing a change of operator basis. And lastly, we showed how you can implement this operator onto circuits using this Walsh function method. And so just to remind you, now that the talk is over, there are 2 things that you should walk away from this. And one is that naively implementing this theory using only physical states, a Hamiltonian that only has physical states in the Hilbert space, has an exponential volume scale on the gate count. And this is prohibitively expensive, but this can be made polynomial by performing a change of operator basis. And so with that, take any questions. Yeah, James.
First of all, thanks. It was a really nice talk. So this whole like rotor formalism that you start with, like, how is it known if that works in other like higher 3 dimensions or not? Say U1, but something more complicated?
Yeah, so for the number of dimensions, this has been worked out. You get different constraints on your magnetic field because it's now a vector and you have more closed surfaces. So I'm glad you asked this because I had it as a backup slide in case someone did. So for 3 dimensions, right, the magnetic field is a vector and you need to make sure that it has 0 divergence through all independent closed surfaces on your lattice. So you also get this constraint on all of the cubes of your lattice that the sum of magnetic field, out and in has to be 0. So these are sort of local-ish constraints on your magnetic field. But you also have these global constraints still, because you have these sort of 2D slices through your lattice. You need to make sure that there's 0 divergence through these as well. But yeah, this has been studied. And to answer the second part of your question, you might want to talk to Christian because he is currently working on how to figure it out for SU2 and higher extensions, but that has not been worked out yet.
Yeah, so we haven't figured out an exact representation of that. So there are other ways to do it, but
it doesn't carry over really. You don't get rotors for non-abelian groups. You can, they just don't have the nice properties that makes it the point of doing that.
Mm-hmm.
Yeah.
Okay, yeah, sure, go ahead, on Zoom.
Jean-Ling, go ahead.
Yeah. Sorry for this question. I think you mentioned, so how to decide the number of the qubits until? What factor decides that number?
Yeah, so as Christian sort of said, you can make arguments that as you increase this number, you should get exponential convergence to the exact answer, but in practice, I think you would have to do the calculation with various numbers of qubits and see if your answer changes by some significant amount or not.
Okay, so is that related to the accuracy of the magnetic field? No?
What do you mean accuracy of the magnetic field? Sorry.
So I mean more until will be more accurate for you to describe the magnetic field. They are not related, right?
Oh yeah, well, as you increase the number of qubits, I would say you represent these operators more closely to their infinite dimensional versions, right? So you truncate them by choosing an NQ and putting it on the quantum computer. But as you use more qubits, you are representing these operators more closely to the undigitized form.
Oh, okay, got it. Thanks.
Yeah, thank you. Sure, yeah.
What changes, if anything, in this formulation once you start introducing charges?
So once you introduce charges, this part sort of stays the same, but you can introduce charges, and so also in this paper here they also talk about this, how to do it with charges, but you would also have to include your pieces for the fermions, and yeah, but they do it in such a way that I don't understand this completely, but they do it in a way such that the longitudinal component of the electric field does not contribute. It doesn't appear. So this is equivalent to like picking the Coulomb gauge. And so that's why sort of and then you can define your rotors such that you get the transverse piece by taking the curl of them. So this stays the same, but you just have to introduce your charges in sort of separate independent Hamiltonians from these terms.
So just a quick follow-up on that question. When you introduce fermions, is there also an exponential scaling that you have to overcome?
I haven't worked it out, but my guess is not, because fermions are small. These are, they're represented by, they're 2x2 matrices because of their statistics. So my guess is no, they would be easy. No exponential scaling.
Cross terms when you square it.
Do we have any further questions for Chris? Okay, I don't see any, but Chris will be here for a few more weeks.
Yeah,
right?
yeah.
So you guys are welcome
sure.
to discuss.
Yeah, feel free. Yes.
Okay.
All right.
Thank you.
Thank you.
I'm really interested that
So
you
then
guys have B as an operator.
Sure.
Mhm.
Like I feel like most